morning everyone. I hope you are all doing well. My name is Dr. Amar Kumar De and I am excited to welcome you to today's lecture titled Frequency Modulation, Equation and Bandwidth for the course Fundamental of Communication System and its Application. It's exciting to see you, so many of you joining us from different corners of the world. First and foremost, I want to extend a warm thanks for taking the time to be a part of this lecture. As we begin today's lecture, let's take some moment to summarize what we covered in our previous session on Introduction to Angle Modulation, FM and PM for the course Fundamental of Communication System and its Application. In our previous lecture, we started with an introduction to modulation, emphasizing its definition and importance in communication system. Next, we outline the two main types of modulation, amplitude modulation and angle modulation. We then defined angle modulation, explaining that it involves varying the phase or frequency of the carrier wave that brought us to the two types of angle modulation, that is the frequency modulation FM and phase modulation PM. For frequency modulation, we explored its basic concept where the frequency of the carrier waves varies according to the amplitude of the input signal. Moving on to the phase modulation, we explained how phase modulation works by varying the phase of the carrier wave according to the amplitude of the input signal. We then compared FM and PM, discussing these similarities, their differences. Then we recapped the key points of the lecture, summarizing the essential aspects of angle modulation, FM and PM, and their significances in modern communication system. With this summary, we are now ready to delve deeper into the specific aspects of frequency modulation, focusing on its equation, bandwidth requirement in today's lecture. So, without further delay, let's move on to the topic titled Frequency Modulation, Equation and Bandwidth. In today's lecture, we will cover several key aspects of frequency modulation. First, we will discuss the basic concepts of FM, followed by its mathematical representation. Next, we will explore the bandwidth requirement of FM signal using Carson rule. We will also look at some common applications of FM and touch on its historical development. Finally, we conclude with a summary of the key point discussed. With this overview in mind, let's move to understanding the basic concepts of frequency modulation. First of all, we have a brief introduction. In today's discussion on frequency modulation, we particularly focus on its equation and bandwidth requirement. Again, just to recall, modulation is a fundamental concept in communication system and understanding it is crucial for any aspiring engineer in this field. Till now, we are aware of the term modulation. It allows us to efficiently transmit signals over long distance and through various mediums. Although various types of modulation are there, now the frequency modulation holds a significant place due to its widespread use in radio broadcast and other applications. By the end of this lecture, you should have a clear understanding of the mathematics underpiping of FM, how bandwidth is calculated for FM signal, and why this is important in practical applications. Let's get started with the basic concepts of frequency modulation. Frequency modulation, or FM, is a type of angle modulation where the frequency of the carrier wave is varied in proportional to the amplitude of the input signal, also known as the modulating signal. This variation in the frequency encodes the information of the input signal onto the carrier wave. To put it simply, in FM, the carrier wave's frequency changes in response to the amplitude of the input signal. When the amplitude of the input signal increases, the frequency of the carrier wave increases, and when the amplitude decreases, the frequency decreases. This method of modulation is particularly useful because it provides better noise immunity, high fidelity compared to amplitude modulation, AM. After getting the knowledge of these basic concepts, it's time to discuss the basic working principle of FM. In frequency modulation, the instantaneous frequency of the carrier wave is given by f of t is equal to fc plus kf into m of t. If you look at this particular equation, it is very clear that in the absence of any message signal, the carrier remain unmodulated and its instantaneous frequency is equal to the carrier frequency. It is the important outcome from this particular equation. In this particular equation, here f of t is the instantaneous frequency of the modulating signal, fc is the carrier frequency, kf is the frequency sensitivity, m of t is the message or the modulating signal. This relationship indicates that the frequency of the carrier wave varies according to the message signal, encoding the information onto the carrier wave. Now, to have a better understanding of FM concepts and to delve deeper into frequency modulation, let's derive its mathematical representation. The instantaneous phase of carrier wave in FM is given by theta of t is equal to 2 pi integral f of t dt. Here f of t was the instantaneous frequency. Substituting the values of this instantaneous frequency in this integral and solving it, we will get it as 2 pi fct plus 2 pi kf integral m of t dt. Thus, the final FM equation will expressed as s of t is equal to a cos 2 pi fct plus 2 pi kf integral m of t dt. Here, s of t is the FM signal, a is the amplitude of the carrier wave, fc is the carrier frequency, kf is frequency sensitivity, m of t is the modulating signal. This equation shows that the phase of the carrier wave is modulated by the integral of the modulating signal. The term 2 pi kf integral m of t dt represents the phase deviation, which is directly proportional to the amplitude of the modulating signal. In order to have deeper concepts of FM, let me explain the key terms in this FM equation. For that, I have to break down some of the key terms in FM multitone equation, which was expressed by s of t is equal to a cos 2 pi fct plus 2 pi kf integral m of t dt. So, in this equation, if we take a look into the angular parameter, we have the carrier frequency fc. This is the unmodulated frequency of the carrier wave, which serves as the reference frequency for FM signal. Next term is the frequency sensitivity kf. This term determines how much the frequency of the carrier wave will vary in response to the modulating signal. It is a measure of the extent of the frequency deviation. Understanding this term is crucial for grasping the concepts of frequency modulation and its practical implementation in communication system. Up to this point, we have explored the fundamental principles of frequency modulation. It includes its basic concepts and equation. Now, let's shift our focus to a critical aspect of frequency modulation, the bandwidth requirement for transmitting FM signal. Understanding the bandwidth of an FM signal is crucial for efficient spectrum utilization, ensuring that communication system operates effectively without causing interferences with adjacent channel. This brings us to an important concept known as Carson rule. Carson rule provides a practical and widely accepted approximations for calculating the bandwidth of an FM signal. By applying this rule, we can eliminate the bandwidth necessary to accommodate the frequency variations of an FM signal, thereby facilitating better planning and management of communication channels. According to Carson rule, the total bandwidth B of an FM signal is given by B is equal to 2 times del F plus FM, where del F is the peak frequency deviation and FM is the maximum modulation frequency. This formula indicates that the bandwidth of an FM signal depends on both peak frequency deviation and the highest frequency present in the modulating signal. In this, the frequency deviation is the amount by which the phase of the carrier wave is shifted from its reference position. In FM, the phase deviation is proportional to the integral of the modulating signal. To derive this formula, we consider the frequency component generated by the modulation process. In FM, the modulating signal causes the carrier frequency to deviate, producing sidebands at frequency Fc plus minus n FM, where n is an integer representing the harmonics number. The significant sidebands are those within the range of the peak frequency deviation del F. Thus, the total bandwidth can be accommodated by considering the highest frequency component, which is Fc plus del F plus FM. Doubling this range to account for the negative frequency gives us the Carson rule, that is, the bandwidth is equal to twice of del F plus FM. This approximation is practical and widely used, though it is important to note that it may slightly overestimate the actual bandwidth in some cases. Now, as we have already covered the important concepts of bandwidth requirement of FM, it's time to discuss the common applications of FM in radio broadcast and telecommunications. So, frequency modulation has several important applications, the most well-known being in radio broadcasting. FM radio is widely used because it provides high fidelity audio transmission with reduced noise and interferences compared to that of AM radio. In FM broadcasting, the information signal modulates the frequency of the carrier wave, which makes the signal less susceptible to amplitude variations caused by electrical noise, atmospheric conditions, and other forms of interferences. This results in a much clearer and much consistent audio quality, which is why FM is the standard for music voice broadcast. The ability of FM to maintain signal integrity over long distance through various obstacles makes it ideal for radio broadcast. FM signal can travel through buildings and natural obstacles with minimal degradation, providing listeners a reliable listening experience even in urban environment with many potential sources of interferences. Additionally, FM wideband allows for transmission of stereo sounds, which enhance the listener's experience by providing a rich and more impressive audio. In telecommunication, FM is used in various wireless communication systems, includes two-way radio, mobile phone and satellite communications. Two-way radio such as those used by police, fire services and other emergency response relies on FM clearly and reliable communications. FM's robust against noise and signal degradations assures that vital information can be transmitted, received accurately, which is crucial for emergency situations. Moreover, FM is used in other applications such as telemetry, remote control system. In telemetry, FM is used to transmit data from remote or inaccessible locations to monitor stations, such as in space exploration, where data from spacecraft is sent back to Earth stations. Remote control systems include those used for controlling drones and model aircraft, relies on FM for precise and reliable signal transmission. In summary, FM wide range of applications in radio broadcast and telecommunications underscore its versatility and reliability for providing high quality audio for radio listeners to ensure clear and dependable communication for emergency services and global satellite networks. FM plays a crucial role in modern communication system. Its ability to minimize noise and interferences coupled with its capacity for long distance signal transmission make FM an indispensable tool in our connected world. Now, as we delve deeper into the significance of frequency modulation, it is essential to understand its historical context and development. Edwin Armstrong's contributions to the field of communication cannot be overstated. Armstrong was driven by the desire to improve the quality of radio communication, which at that time was dominating by amplitude modulation. His pioneer work in FM marked a turning point in the field of communication, offering a solution that significantly reduces the noise and statistics that plagued AM broadcasting. His invention laid the foundation for the modern radio broadcast and many other communication technologies. Armstrong's work did not stop at the invention. He has also worked in demonstrating the practical applications of FM. Despite facing initial resistance from stabilized AM broadcasters who were reluctant to change, Armstrong persistently paid off through numerous demonstrations and improvement. He proved that FM was a superior form of modulation, leading to its widespread adaptation. The development of FM by Armstrong was not just a technical achievement, it was a significant advancement that transformed the way we communicate. It opened up new possibilities for high fidelity audio transmission and reliable long distance communication, setting the stage for future of broadcast and telecommunication. Armstrong's impact extends beyond just improving radio broadcast. His work influenced the development of various communication systems, including television sound, two-way radio, cellular communication. FM robustness and clarity has made it a perfect choice in this and other applications, solidifying Armstrong's legacy as a pivotal figure in the history of communication technology. Now that we explored the historical backdrops and significances of FM, let us move on to the interesting part of this lecture, that is the importance of understanding FM in communication system. Understanding frequency modulation FM is crucial for anyone involved in communication engineering. FM is not just a technical concept, it is a fundamental aspect of modern communication system that underpins many of the technologies we rely on today. First, FM provides high fidelity audio transmission. This means that the sound quality is much clearer, much accurate compared to other modulation techniques like amplitude modulation. In FM, the information signal modulates the frequency of the carrier wave rather than its amplitude. This makes FM less susceptible to noise and interferences, which are common issue in AM transmission. The result is more consistent and reliable audio signal, which is why FM is preferred method for broadcast, music and voice over the radio channels. The clarity of FM audio transmission has set the standards for what listeners expect from radio broadcast, contributing significantly to a widespread adaptation. Moreover, FM plays a vital role in various wireless communication systems. In telecommunication, FM is used in applications such as two-way radios, mobile phone and satellite communications. For example, emergency services like police, fire department and medical responder relies on FM two-way radio for a clear and reliable communication. The robustness of FM ensures that critical information can be transmitted and received accurately, even in challenging environments. With the help of this technology, which provides us with high level of noise and interference suppression. This reliability is essential for coordinating response during emergency and ensuring public safety. In mobile communication, FM technologies has been utilized in analog system and continue to influence modern digital communication techniques. FM principle is foundation to understand more complex modulation systems used in cellular networks. Satellite communication systems also benefited from FM ability to maintain signal integrity over long distances, provided reliable links between ground station and satellite orbit, the Earth. This enables a wide range of applications from global broadcasting to GPS navigations. Furthermore, FM robustness and efficiency make it a cornerstone of modern communication technology. The ability of FM to maintain signal quality over long distance and through various obstacles is significantly advanced. This robustness comes from FM resistance to amplitude variation caused by noise, which means that the transmitted signal remains stable and clear even in adverse conditions. This characteristic is particularly important in environment where maintaining high quality communication is critical, such as in aviation, maritime and military applications. FM efficiency in utilizing the frequency spectrum also contributed to its importance by effectively managing bandwidth and reducing interferences. FM enable the transmission of multiple signals within a limited spectrum. This efficiency is crucial in today's crowded communication landscape, where the demand for wireless communication channel is constantly increasing. In conclusion, a deeper understanding of frequency modulation is essential for anyone involved in communication engineering. FM ability to provide high fidelity audio transmission, its crucial role in various wireless communication systems and its inherent robustness and efficiency makes it a fundamental technology in modern communication. Mastering FM principle not only equipped engineers with the knowledge to design and optimize current communication system, but they also lay the groundwork for future innovation in this field. This elaboration emphasizes the critical importance of understanding FM in communication system, highlighting its application, advantages and overall impact on modern communication technologies. Now that we explored the important concept, historical backdrop, significances of FM, let's move to the final part of this lecture, that is the conclusion part. As we conclude our discussion on frequency modulation FM, let's summarize the key points covered in this particular lecture. We began with an introduction to modulation, emphasizing its importance in communication system. Modulation is crucial for efficient transmission, better bandwidth utilization, noise reduction, multiplexing and frequency translation. Specifically, frequency modulation FM was highlighted as a key modulation technique due to its ability to reduce noise and improve signal quality. Next, we delved into the basic concepts of frequency modulation. Involves varying the frequency of the carrier wave in accordance with the amplitude of the input signal. Moving forward, we explored the mathematical representation of FM. The FM equation is derived from the relationship between carrier waves, frequency and the input signal. We discussed key terms in FM equation such as the carrier frequency, the frequency deviation, which collectively determine the characteristic of FM signal. We then examine the bandwidth of FM signal, focusing on the Carson rule, which provides a practical approximation of bandwidth required by an FM signal. The bandwidth of an FM signal is determined by the modulation index and the highest frequency present in the modulating signal, ensuring that the transmitted signal occupies a specific portion of the frequency spectrum. Following this discussion, we also discussed the various applications of FM. FM is widely used in radio broadcast due to its ability to produce high fidelity audio transmission with reduced noise and interferences. It also finds application in various telecommunication systems, including two-way radio, mobile phone, satellite communication, owing to its robustness against noise and signal degradation. We then move on the detailed equation and bandwidth analysis. We examine the FM equation and its parameter, providing insights into how FM signals are generated and transmitted. Understanding the bandwidth requirement for FM signals help us in designing efficient communication system that makes optimum use of the available frequency spectrum. Finally, we discussed the historical context and development of frequency modulation. It was invented by Edwin Armstrong in the year 1930s as a solution to the limitation of AM broadcast. Armstrong's contribution revolutionized the radio communication, improving audio quality and transmission reliability. His persistent efforts led to the widespread adaptations of FM as a superior modulation technology. By grasping these key points, we can appreciate the technical foundations and practical applications of frequency modulation in modern communication system. FM continues to play a crucial role in ensuring clear, reliable, and high quality transmission of information across various media. Before we conclude, I would like to take a moment to thank all of you for your participation, attention throughout this lecture. Your engagement and curiosity makes this session truly rewarding. I appreciate your decision to learn and hope that today's lecture has provided you with a valuable insights into frequency modulation, equation, and bandwidth. Once again, thank you for joining today's lecture. I am looking forward to see you in our next class. Take care. Have a great day. Thanks all.